Hello everyone, I welcome you to lecture 27 of Math 22. This lecture contains three topics: arc length formula, parametrization using arc length, and curvature of space curves. I will divide the lecture into two sections, and in this video, I will talk about arc length and parametrization using arc length. Let us begin. Recall that in the two-dimensional space, a given curve can be parametrized by a pair of equations, x equal to x of t and y equal to y of t. Now, if we take a particular interval for t, say the interval t equal to a to t equal to b, we can compute the length of the arc on the curve on that interval. And it is given by the integral from a to b of the square root of x prime squared plus y prime squared. Note, however, that we can use this formula only when the curve satisfies two conditions. The first condition is it must be traced or traversed exactly once from t equal to a to t equal to b. And the second condition is that the curve must be smooth anywhere from t equal to a to t equal to b. Recall that smoothness is attained when dx dt and dy dt are never both zero on the said interval. We can extend this formula to curves in the three-dimensional space. Suppose that a curve is parametrized by the set of equations x equal to x of t, y equal to y of t, and z equal to z of t. Or equivalently, the vector equation r of t equal to x of t, y of t, z of t. We can compute the length of the arc on this curve on the parameter interval ab using the formula integral from a to b of the square root of x prime squared plus y prime squared plus z prime squared with respect to t. Observe that the formula is very similar to that in the two-dimensional space, except that we add a third component or a third coordinate. This formula can be used only when the curve satisfies the two conditions. Number one, it must be traced exactly once from t equal to a to t equal to b. And number two, it must be smooth anywhere between t equal to a and t equal to b. In the three-dimensional sense, smoothness of a curve is guaranteed by the non-zero value of the derivative r prime of t. And from now on, we will be denoting the arc length by the small letter s. Observe here that the integrand in the arc length formula is actually a very familiar expression. It makes use of the derivatives x prime, y prime, and z prime. Can you tell me what this expression is? Right. It is equal to the norm of r prime of t. Hence, we can rewrite the arc length formula simply as the definite integral from a to b of the norm of r prime of t. Let us use this formula to answer the next two examples. For our first example, consider the helix represented by r of t equal to cosine t sine t t. Let us find the length of the arc on this helix from the point where t is equal to 0 to the point where t is equal to 2 pi. Before I proceed to computing the arc length using the arc length formula, I have to verify that the two conditions are satisfied. First condition clearly is satisfied. It is traced exactly once from t equals 0 to t equal to 2 pi. Why? Because the third component here of r of t is t. So there is a one-to-one correspondence between these values and the third component of this vector function. For the second condition, we compute r prime of t. Differentiating every component of r, These are the components of R prime of t. Take a look at the third component. The third component is 1, which is a constant and is non-zero, which means that for any value of t between 0 and 2 pi, this R prime will never be equal to the 0 vector. Hence, smoothness is guaranteed. We can now proceed to computing the arc length using the formula. The integrand contains the norm of R prime of t. With this R prime of t, we compute its norm. The norm is equal to the root of the sum of the squares of R prime, the components of R prime. Simplifying this, it gives the constant function square root of 2. Hence, the arc length, which we denote by S, is equal to the definite integral from 0 to 2 pi of the function square root of 2. Well, this is very easy to integrate. You just multiply the square root of 2 by t, and you evaluate this from t equal to 0 to t equal to 2 pi. We get the number 2 times the root of 2 times pi. Hence, the length of the arc on the helix corresponding to the given parameter interval is 2 times the root of 2 times pi units. Let us consider another example. The curve is defined by the vector function r of t with the following components. Compute the length of the arc on this curve from the point where t is equal to 0 to the point where t is equal to 2. So again here, we have to verify that the two conditions are satisfied. First condition, again, is satisfied. It is traversed exactly once from t equal to 0 to t equal to 2. That is because this is 1 to 1. The second condition requires us to compute r prime of t. Differentiating every component of r here, so this component will have derivative equal to 6t to the 1/2. The second component has derivative 3 cosine t, and the third component has derivative 3 sine t. Observe that the second and the third components will never be 0 at the same time. Okay, there is no value of t for which both cosine and sine is 0. Hence, r prime is never the 0 vector. Smoothness is guaranteed. So again, we have to compute the norm of r prime of t, and we will use that as the integrand in the arc length formula. Simplifying this, the first term, when squared, is equal to 36t. The second and the third, when combined, is equal to 9. So this is equal to the square root of 36t plus 9, which we can also write as 3 times the square root of 4t plus 1. Hence, the length of the arc on the given interval is the definite integral from t equal to 0 to t equal to 2 of the function 3 times the square root of 4t plus 1. Now, to find an antiderivative for the square root of 4t plus 1, you can use a simple substitution on 4t plus 1. Say, you can let u be equal to 4t plus 1, and then you transform everything in terms of u, you find an antiderivative. I will leave that to you as an exercise. You can verify that one particular antiderivative for this is 1/2 multiplied by 4t plus 1 raised to 3 over 2. Evaluating from t equal to 0 to t equal to 2 will give us the following result. I am factoring out 1/2. 27 is the value of 4t plus 1 to the 3/2 when t is equal to 2. And 1 here is the value of 4t plus 1 to the 3/2 when t is equal to 0. This now simplifies to 13. The length of the arc is therefore 13 units. Computing arc lengths is not the only purpose of the arc length formula. In fact, we can use that formula to find a representation of the space curve using the arc length as the parameter. Generally speaking, when we have a vector function r of t, this parameter t may or may not possess a physical or geometric meaning. But in some cases, in particular, for motions along a curve, the convenient parameter we use is the time parameter, meaning I am letting t be a time value and r of t the position vector. So that means if I am given a specific time value, I can locate the object that moves in the space along the curve or along the graph of r of t. Its position will be the tip of the vector r of t. But for geometric properties of the curve, the most convenient parameter that we can use is the arc length parameter s. So our goal for the next part is, given an r of t, we want to find another representation by replacing t in terms of s. Take a look at this illustration here. I have a curve in the three-dimensional space represented by r of t. I am going to pick a reference point. The reference point has parameter value t naught. Okay, so that is the point on the curve, which is the tip of the vector r of t naught. Now, if I'm going to take an arbitrary value for t that is greater than t naught, then I will be getting a point that lies somewhere here. Say this point here. Okay? So the tip of the vector r of t will be somewhere here, and we can consider the length of the arc on the curve starting from r of t naught towards r of t. That length will be denoted by s. Here we can see that we can actually relate the parameter t and the arc length s. We can see here that when this value of t is very close to t naught, then s would be very close to 0. Or if t is very far from t naught, then this s becomes very large. So how do we relate, or how do we find a nice relation between s and t? We are going to use the arc length formula. So choosing t naught as our reference point, we consider this arc length formula. The length of the arc from the parameter value t naught to an arbitrary parameter t greater than t naught is equal to the following definite integral. So here, we are writing s as a function of t. And note that in the given vector function, I am now using a dummy variable u, since we are using t as the upper limit of integration. Observe that in this integral function, s is considered as the directed arc length on the curve on the interval from t naught to t. And moreover, s is a differentiable function of t. In fact, by the first fundamental theorem of calculus, I can solve for the derivative on both sides with respect to t. On the left-hand side, I will get ds dt, and by FTOC, the derivative of this with respect to t will just be the integrand evaluated when u is equal to t. And so we will have ds dt equal to the norm of r prime of t. Furthermore, s is an increasing function of t. Well, because of the smoothness of the curve, this norm of r prime of t will never be equal to 0, since r prime is not the 0 vector. And because it is a norm, it now tells us that ds dt is always positive. If the derivative is positive, then this must be an increasing function. Moreover, s is a one-to-one function of t. So from here, we are writing s as a function of t, which is one-to-one, and therefore invertible. It has an inverse, which means that we can write t as a function of s. If t is a function of s, let that function be, let's say, phi of s. We may now rewrite this vector function r of t by replacing t by phi of s. So r of t is equal to r of phi of s. Hence, this is now a vector function that is dependent on s. We are going to rename the vector function as r star of s. This is now called the arc length parametrization of the vector function r. So what is the purpose of this arc length parametrization? Well, it helps us easily locate an object along a curve given an arc length measured from a reference point. Let us consider an example. In this example, we are using the helix with equation r of t equal to cosine of t sine t t. The first problem asks us to rewrite this vector function r using the arc length as a parameter with reference point 1, 0, 0. The given reference point 1, 0, 0 clearly corresponds to t naught equal to 0. Well, because the third component of r is t, and the third coordinate of the reference point is 0. Moreover, in the first example, we have seen that the norm of r prime of u is the constant function square root of 2. Using now the relation between s and t, we set up s equal to the integral from the reference value t naught to an arbitrary t of the norm of r prime of u, which is equal to this. Reference value t naught is equal to 0. Norm of r prime of u is equal to the square root of 2. This is equal to the square root of 2 times u. U is evaluated from 0 to t, which now gives us the function square root of 2t. So we are able to write s as a function of t. We can now write t as a function of s. We simply divide both sides by the square root of 2 and get t equal to s over the square root of 2. We can now rewrite this given vector function r as r star of s by replacing every t that you see here by the expression s over the square root of 2. Hence, r star of s will have the following components. For the follow-up question, we want to find coordinates of another point on the curve, name it the point Q, given that the arc from the point P to the point Q along the increasing values of the parameter has length equal to the square root of 2 pi units. Since in item A, we used P as the reference point, then this given square root of 2 pi actually corresponds to the arc length S. We are simply looking for the value of r star when S is equal to the square root of 2 times pi. Okay, and by plugging in square root of 2 pi in place of S, we now get the vector -1, 0, pi. Hence, the point Q that we are looking for has coordinates -1, 0, pi. Let's have another example. Let us parameterize using arc length the vector function r of t with components 4t to the 3 halves, 3 sine t, and 3 cosine t with reference point where t is equal to 2. From the second example, we have seen that the norm of r prime of u is equal to 3 times the root of 4u plus 1. Hence, using this formula for s in terms of t, we replace this t naught here by the reference value 2, and we get the following integral. You can check that an antiderivative for this function is 1/2 times 4u plus 1 to the 3 halves, and we evaluate u from 2 to t. We get the following expression. This is the value when u is equal to t. This is the value when u is equal to 2. 1/2 is factored out. We are able to write s as a function of t. We get the inverse. T in terms of s is now equal to 2s plus 27 to the 2/3 minus 1 over 4. Hence, we can rewrite this r of t as the function r star of s by replacing every t here with the following expression. We get the new parametrization in terms of the arc length parameter s. I am going to end this lecture with some remarks. The arc length parametrization is the most convenient parametrization that we can use because it is unique up to starting point and direction. If I'm going to give you a specific reference point and a direction of the traversal of the curve, there is exactly one parametrization corresponding to that. The arc length parametrization has the property that the norm of its derivative is equal to 1. We call it a unit speed curve in this case. Moreover, the unit tangent vector t of s is equal to the derivative of r star of s. That is because there is no need to normalize r star prime because its norm is already equal to 1. We can check whether a given vector valued function is already arc length parameterized by inspection on the norm of its derivative. The norm of its derivative is equal to 1 if and only if it is already arc length parameterized. As a particular case, if we have a line in the space passing through the point x0, y0, z0, we can give an arc length parametrization of a line if we use a direction vector of norm equal to 1. That concludes the lecture for arc length formula and arc length parametrization. Thank you.